Hello everyone, today I'm here to present our research work, Dynamic Taxi Rideshare through Adaptive Request Propagation using Original Taxi Demand and Supply. I'm Haoxiang from the University of Texas at Austin. The daily traffic volume is significantly increased year by year, as high housing price in and around the major job center across the country, forcing the people living far and far away from where they work, and have to drive to their workplace every day. Speedily increased traffic makes on-road time significantly increased. Some researchers call the people who spend more than 90 minutes every day are supercommunicators. The right figure shows the percentage of the supercommunicators in every big city. You can see that in some cities, there are more than 10% of the people are supercommunicator, which need more than 90 minutes drive to go to their workplace. The problem is bigger and bigger. The left figure shows the percentage for the supercommunicator increased year by year, especially in a city without a huge public transportation system. This kind of traffic problem is not just for US. Red figure shows in Beijing, China, a lot of taxis waiting in the line just for picking up one passenger from the pickup location to his destination, which is a waste of the resources. We already take a look about the traffic problem in the micro level. Let's take a look about the macro level. These two figures shows the traffic congestion problem happened during the afternoon peak hour. You can observe that there is several major roads has the worst congestion, such as this highway and the highway in the middle, and also the lowest highway. Also on the right figure, you can see like this highway, this one, and this one has the most traffic. And we can simply understand that the people using this highway are from a similar location to a similar destination. We believe that the rideshare is one of the best solutions for this kind of growing traffic congestion problem. As the passengers are spatial-temporal co-located, we can easily combine them with a reasonable and predictable detour time. The rideshare can reduce the single trip and also has a good benefit for the driver and the passenger. Rideshare is not just a new idea, it has been used in reality for several years. However, most of today's rideshare systems are using a centralized approach, such as Uber and Lyft. This kind of centralized system are using a central server to process, match, and schedule the trips. When the passenger sends the request will be received by the central server, and the server will find the best taxi and return the information to the passenger and also send the departure request to the taxi. There is another type of the rideshare framework has been researched in recent time, the distributed approach. In the distributed approach, there is no central entity. The message is exchanged directly between the taxi and the passenger through the broadcast way. However, there is a drawback for both approaches. For the centralized approach, it is in danger of a single point failure. When the central server down, the whole system out of services. The passenger cannot get to their destination and the driver cannot get any benefit. This is not just assumption, it really happened several times, such as several years ago in Beijing, the DD is down for several hours in the morning peak hour, makes a lot of people cannot go to their workplace on time. On the other hand, the distributed approach facing a problem with a low successful rate, and some taxi in the urban area cannot receive enough requests. In this paper, we propose a hybrid approach to attempt to address the drawback for both distributed and centralized approach. Our contribution for this paper are listed below. First, we propose a novel adaptive transmission range control system, which automatically fine-tuning the transmission range by using the passenger's feedback. This structure can reduce the low successful rate problem with the distributed approach. Also, the system is working completely on a distributed manner, which also solves the drawback for the centralized approach. There isn't a single point failure problem. To prove the success of our system, we simulate our system using a Chicago taxi dataset and shows that the adaptive transmission range can successfully control the message propagation and corresponding the processing overhead for taxi ride share, and also as a side effect, the system can reduce the passenger waiting time, will also improve the taxi utilization. Let's take a look about the distribution for the taxi ride Chicago taxi demand. This figure shows the spatial distribution for taxi pickup and drop-off location for Chicago area. You can see that 4 out of 77 community area has the most request, and the rest of area has almost zero demand. You can see this area, this one, and this one has the most request, and also airport has the most request. Let's convert the figure to the map. You can see that the central area and the airport has the most request. The area near the central area has a few requests, such area in the top. And the other area almost has 0 requests. Based on the information we present above, we will separate the area to dense area, target area, and sparse area. Our system are mainly focused on the target area because the taxi in the dense area already receive a significant amount of requests with a high successful rate. And it's almost impossible for us to improve the successful rate for the sparse area due to the request is too less. Then let's talk about more detail about our system model and the messenger exchange procedure. The left figure shows the passenger 1 provides the information for if his trip successfully matched or not to the TX server and his pickup area. Then, when the passenger P2 wants to send his request, he will send a TX query to the central server with his pickup area ID. The central server will return the best TX to P2, and the P2 will use this TX to send out his request information to the nearest taxi. This is the step 1, step 2. And in the step 3, the passenger, this one is a P2. He begins send out the request message through a localized communication. In this simple figure, 3 taxis receive the request. And then taxi will process his request, see whether they can pick him up or not. If they can, they will send a reply message to the passenger. Then passenger has a 3 choice. Based on a predefined scenario, the passenger will choose the best taxi. Then he will send back the confirm 1 message to the target taxi and let him know he chose them. Because the dynamic nature of our system, the taxi may move, and his seat may already taken by some other passenger, so that the taxi need to verify again to make sure he still be able to pick up this passenger. So he will process the request 1 more time. If he still can do it, he will send back the confirm 2 message. In the meantime, the passenger's information has added to this taxi's permanent queue, and taxi begin to drive to the passenger's location and pick him up. The main purpose for the central server is to let the message reach to the best amount of taxi that can let them to get the highest successful rate and without the message exposure. So on the left one, you can see in a peak area or in a peak time, the passenger only need to use a small TX range, let 3 taxis to receive his information. But on the right figure, on the non-peak area and non-peak time, because there isn't enough taxi in this area, the passenger need to use a larger TX to let the passenger receive the information. So the TX is the range. Also, for the TX range, on the central server side, the demand forecasting model has been built in. We are using a Proforce model as a forecasting model to predicting the next hour situation with the information received from the passengers, as the P1 we talked before. We simulate our model by using the real text data from Chicago area on June 19, 2019. The one-day data contain a lot of trip with 77 community area. During the simulation, we also attempt to using a different transmission range, TX, and different number of taxis. To measure the performance of our system, we are using 4 different performance metrics listed below. First is a localized successful rate, which focuses on the success rate for a particular community area. Next is a taxi activation ratio. This one is describe how many taxis has been really used in the system in the 1 day of simulation. The average occupancy ratio is used to measure how many times the taxi has 2 or more passengers, which means the ride share really happened. The average waiting time is measure the time between the passenger send out the request and the passenger has been picked up. So there is 2 times has included in here: the message process time and the time from the taxi current location to the passenger pickup location. Then let's take a look about our result. Keep in mind, we are trying to log our successful rate inside of the purple line, which is this one, and the yellow line, to find the balance between the successful rate and message overhead. You can observe that for the dense area, when you compare A1, A2, A3, you can observe that with a different taxi number, if there's more taxi in the system, the less transmission range is needed. If you compare A1, A4, A2, A5, A3, and A6, you can observe that whatever the TX has been initialized, it will reach to the almost the same amount of TX after some time. So you can see on the A1, 2, 3, we initialize the TX with 100. And on the lower 3 figure, we initialize the TX on the 600. But after some time, they will reach to almost the same TX level. And this pattern actually is also be shown in the next several figures. For the target area, everything begins different. To get a high successful rate, TX need to be increased really quick to even reach to the max after some point. Like the 2 kilometers max, so this line is already reached to the max. If there is more taxi in the system, the speed of the increase is much slower than it with less taxi. Compared with the previous slide, you can see that the target area need a bigger TX range, and the successful rate is a little bit hard to maintain. You can see in this area, the success rate already lower than our target area because the TX already reached to the maximum. Similar for this figure, but for the area with enough taxi, you can see it's still maintaining our target level. Unlike the dense and target area, the successful rate is much harder to maintain for the sparse area. You can observe that the TX is already reached to the maximum, but the success rate is really low. It's around 50%. And it's really unstable. Sometimes really high, really low, because there isn't enough request in this kind of scenario. Also, when you compare our result with the previous distributed ride share system, you can observe that the current proposed rideshare system has a low waiting time and a higher taxi activation ratio. Due to the higher taxi activation ratio, the average occupancy ratio is slightly reduced than before. However, the average occupancy ratio is still higher than 60%. You can see here, which means more than half of the trip time has been done in a rideshare manner, which is which is good for the whole city and the whole environment. Thanks for listening. If you have any question, please feel free to reach out me at email listed on screen. I'd be happy to help. Thank you.